Okay, good afternoon. I have the pleasure of introducing our speaker today. I'm also going to take a second just to introduce myself. Many of you here know me, but many of you probably don't. So I'm Eric Kalachik. As of last Wednesday, literally 1 week ago, I am director of the Hariri Institute. It has been like drinking from a fire hose, if you're wondering, but it's been a blast. I'm very much looking forward to working with people across campus in this capacity. So if you don't know me, I'm a statistician by training. My original background was in mathematics, migrated statistics. Have dwelt heavily at the interface with engineering, did digital signal processing for a long time, and then eventually moved into network science about 15 years ago. That's been the venue by which I've worked with people from the social sciences to the humanities to the medical sciences to neuroscience and whatnot. So John Tukey, a famous statistician from the 60s, of course, is well known for saying that statisticians are lucky because they get to play in everyone's backyard. I've enjoyed doing that the last 20 years here at BU, and through directing the Hariri Institute, I'm essentially looking forward to playing together in everyone's backyards as we move computing and data sciences at BU to a new level. That really is my charge. The one that I took on is to move the Hariri Institute to national visibility. That means bringing you to national visibility. And in a very ironic sort of sense, in terms of the computing and data sciences, who are the ones who are often leading the charge, right? It's our newest hires who are often the ones who are doing this, right? The rest of us older folks, we learn what we learn. We learn a certain software package, we learn a certain methodology or whatnot, and it's very often the folks who are our junior colleagues who are coming in and leading the way very quickly. So this series is meant to honor those sorts of colleagues. The people who are chosen as Hariri Junior Faculty Fellows are chosen through a highly competitive process. BU, as you know, has become very aggressive, like most institutions, in trying to hire the very best in the space of data science. And so we have amazing people with background in computing and data science all across the university now. Really, BU is computing and data science in many ways. So it's very competitive. It's meant to be an honor. And in turn, it's an honor for us to have them associated with us. I'm particularly looking forward to hearing about the talk. As a statistician, the census was essentially one of the primary and only roles of being a statistician when you go back 150 years. So to have someone who's blending machine learning in the modern era with census data going back decades is, for me, really a treat. I have a small token of appreciation for you. So we have the thing where we have to decide, do I tell him what's in here or do we wait? So I can't tell you the story behind it if I don't tell him what's in there, right? So this is a small lens, right? The lens was adopted by my predecessor, Azar, right? Azar Bastavros. And the idea is that the lens is a symbol meant to sort of show our ability through data and computing to gain insight into the problems in the life around us. So it's a symbol and also a token of appreciation.
Thank you.
All right. So I'm going to turn it over to Bart, who I guess will say hopefully a few other kind words, and also talk a little more authoritatively about the background.
Thank you. So I have to say I feel extremely awkward about introducing James to a room half of whom already know him. I find it particularly awkward to try to say something about his research when that same half of the room knows his research much better than I do. So I feel like if I try to say something about his research, I'm going to be kind of like putting you in the position of Joe Biden supporters wondering what's going to come out of his mouth next. So I think I'm going to stay away from that. And instead, I'm just going to stick to introducing James to the part of the room that don't know him yet. So James spent his academic life as a student and as a faculty member in our neck of the woods. He did his undergraduate at Wesleyan. I can't say it.
You're close.
Wesley, I was very close. I was very close. I told you, James, Joe Biden. There we go. Anyway, Wesleyan University, earning his BA in economics and math in 2008. He then came closer to us and went to Harvard for where he got his MA in economics in 2012 and his PhD in 2016. Then, for some strange reason, he went a little bit further away and went to Princeton as a postdoc for a year, and finally came back to us starting in fall 2017. He's won numerous grants and awards, both as a student and since then, including a Robert Wood Johnson Seed Grant while he was a PhD student, a Russell Sage Foundation grant more recently, and the Alan Nevins Prize for the best dissertation in U.S. economic history, awarded by the Economic History Association in 2016. So with that, let me turn it over to James.
Cool. All right. Thanks, Bart. Thank you guys all for showing up. We're good? Okay. I had one job. I pressed the right button on the mic, and I'm really excited about that so far. Cool. All right. So I want to, full disclosure, I wasn't exactly sure who was going to show up to this, and it seems to actually be a really nice mix of people between economists and non-economists. So I'm not going to present a paper per se, but this will be more of an overview of some of the work I've been doing, essentially to develop the toolkit that we need to generate, as I say, new data from old sources. And in particular, thinking about ways to generate linked census records. When you go back historically, we don't have a lot of clean, nice, pretty longitudinal data. We can follow someone from childhood to adulthood to death. Historically, we usually just have snapshots, and so this is an attempt to kind of improve the data landscape historically. Okay, so cool. And I should say, so I know on the schedule it says 45 minutes and then quick Q&A, but I will go nuts if you guys don't ask questions during traditional econ style. So feel free to yell and interrupt or raise your hand or whatever. Okay, so the sort of the line I like to give on this, and a lot of you have probably heard it before, is that economic historians, we sort of went from this world where we were very data poor, or at least somewhat data poor, to quite incredible and data rich. Some sense you can think of us a little bit like big data genealogists. So we've got, the complete count census has now been digitized and transcribed all the way from 1790 up to 1940. We're very sad to be missing the 1890 census, which sort of got lost in a fire, and then the water that put the fire out also ruined the rest of the census. But from 1790 to 1940, we have essentially a little bit of microdata, it depends which year, how much data we have, about everybody in the country. There's similar efforts to digitize and transcribe records in other countries, other records, and you can kind of think of also these all sorts of other smaller samples of data that we can then link into the census. And now you've got an interesting variable or an interesting set of data about a couple thousand people or tens of thousands of people, and now you can find them in the census and follow them forward or follow them backwards, understand what they were up to after or what they were up to before. And so we're in this new world where we can sort of increase quite a bit the number of questions we can ask. And so I usually, when I give this talk, actually ignore this question of what kind of questions can we now ask and answer and jump right ahead to the stuff I really am going to talk about, which is the methods to how we create these longitudinal samples. But I wanted to actually give a quick detour both into a little bit of my work, but also a lot of others, about the new kinds of questions that economic historians now have the data sets and the tools to try to tackle, just to try to entice you into believing that the stuff that we're doing is cool. So this is a paper of mine where I was able to link we'll learn a lot more about these kids throughout today's talk, a sample of sons from the Iowa 1915 state census, and I linked them ahead to their adult selves in 1940. And so one thing you can't do if you just observe someone at one point in time is understanding anything about intergenerational mobility. How much who your parents were, or what they did, or how much they earned, or how many years of education they had, how does that affect you? If I only see you at one point in time and the census isn't going to ask you when you're an adult in 1940, hey, who were your parents and what were they up to? Those bunch of questions that we can't answer. And so this is data that I linked, basically taking these kids in the 1915 Iowa state census for reasons that are not super important. Iowa's kind of the only state you can do this for in 1915 and has education data and earnings data, and then found them forward and was able to say something about these links between parents and sons, or fathers and sons in this period. You guys have probably all seen this. This is sort of like the famous map. This is not with linked census data per se. This is Chetty et al. Sort of contemporaneous work, trying to understand, again, intergenerational mobility, to graph it across space. This is the kind of map that 5 years ago you couldn't have made for historical data because we just didn't know who the fathers and sons or who the parents and children were across the country. We now can, and so this is Huiren Tan, who's one of Bob and my grad students who graduated last year, put together for his dissertation. This is like not even, this is like basically a side note of all the other stuff that he does in his dissertation, but tries to answer these questions about intergenerational mobility. What does the map of mobility look across the country? And he's able to ask, why does the map look different historically as it does today? What caused this change? Again, you need this linked data to be able to do this. And you need to be able to not just link a few people, but you need to be able to link at scale. So you have enough people in each of these counties to follow them forward. This is work from Anna Azer and co-authors, where they're sort of long-run effects of social insurance. So this is a program called the Mother's Pension. The basic idea is you can, again, follow people as children in the early 20th century. Some of their mothers apply for this social welfare program and are accepted, and some are rejected. And then they're able to say, how did these kids turn out 30, 40 years later when we see them again? What are the long-run values of this policy program? Turns out, we can see the curve shifts a little bit from on log income. They earn a little bit more, and then we see big changes in education as well. The bar, you can see like the spike in 8 years for the rejected sons, and then the sons of mothers who got accepted are more likely to have finished high school. So these are the kinds of sort of classic economics questions. I have another paper with Huiren where we used to do sort of like the classic labor economics thing to try to estimate the returns to education, basically things that all of us, because we're so overly educated, probably really care about. How much is each additional year of education worth on the labor market? And we want to sort of eliminate or to do our best to control for sort of nature and nurture differences. And so we compare two twin brothers, one of whom gets 9 years of schooling, one gets 8 years of schooling. How much more does one earn than the other? Again, really, really hard to do. If I just observe you in 1940 or in any year, I don't know who your twin brother is and how much he earns. But we can go backwards. We can find all the twins in 1900, 1910, and 1920. There's a lot of them. There's not that many. Twinning is relatively rare before IVF, but there's enough. And we can follow them forward, see what they're up to in 1940, and compare them. But it's actually not just like sort of boring economics questions that we can answer with linked data. So this is a project with Andy Hall and two of his graduate students at Stanford, where we link members of Congress backwards to ask the sort of fundamental question of like, who are the people who lead us? Bart's already made some political jokes, so I'm just going to slide right past them. What do we find? Well, like the not surprising fact is these members of Congress tend to be really rich as adults, much richer than the rest of the population. But it's not just them, it's intergenerationally. So when we see their parents, these are the families of these future members of Congress who are under the age of 18 in 1940. I was trying not to do any tables. I like graphs more than tables, but whatever, here's a table. We can see that about 5% of the population is in a family with someone with a college degree. 30% of the future members of Congress are. Half of the members of Congress have someone who attended college compared to 12% overall. Much more likely to earn much more money sort of at every level of the income distribution. So maybe people who run for Congress are super selected. These are questions we couldn't have really answered unless we had access to this complete count census data, and we could go find these people backwards. I have another project sort of in a similar vein with Max Palmer, who's in the audience, trying not to fall asleep, and Ben Schneer, where apparently we don't really have any graphs or tables that I thought would look pretty on the slide, so I'm just going to show you the title in extremely large font. But here again, we link the members of Congress, and we ask sort of a question about how your family background, how your family history affects how you behave in Congress. And so we find are in the early 20th century when there's a bunch of sort of very draconian immigration bills being debated. The borders closed in the US in the 1920s. The kinds of members of Congress who are voting against that tend to be those with family backgrounds that have more immigrants in them. So your grandparents are immigrants or your parents are immigrants. You're much more likely to vote against those kind of bills. Again, questions that like we need to be able to see you in the census and then see your parents in the census and do all these links to sort of understand things about your background. And that's obviously just a small smattering of sort of the papers that I could either find a pretty picture for or a giant title. But there's lots of other sort of really cool stuff going on. These questions that we're now able to ask and answer because we have the microdata that allows us to find these people. And you can kind of think about this, maybe I didn't need millions and millions of records through those members of Congress research. Like we probably could have read a book or something and learned about where those people came from. But it enables us to then pick up a bunch of control people, a bunch of people who lived on their block. In one of the papers, we compare members of Congress to their much less famous siblings, and we can follow them forward as well. So again, the ability to basically see everybody at a 10-year snapshot throughout history enables us to do a bunch more questions. So, okay, now that I've gotten you all really excited about all the things we can do with history, now I'm going to drag you through the methodology, or basically try to answer this question of how do we do it. I want to build these linked data sets. What do we actually have to do to put these things together? And so this is a really sort of not surprising problem. Anyone who's either tried genealogy or literally just had two lists of names on two pieces of paper and tried to figure out who's who. Names are really complicated, and the variables we have to link people historically are not always sufficient. So when we go back in time, we don't have unique identifiers. We don't have social security numbers. The census is never asking you what day you were born. It only is going to ask you basically how old you are. In very rare occasions, it'll ask what year you were born. Once it asks what month you were born. Instead, we sort of have to rely, instead of these sort of great fields that we might be able to use to make really precise identification, on sort of a set of coarse identifiers. So I see your name, I usually see your year of birth, and I see your place of birth. And place of birth in the census, if you're US born, is just a state, and if you're foreign born, it's literally just the country. So I'm not micro-targeting people based on the exact address of their hospital where they were born. And so sometimes this is pretty easy. So this is James Alexander in 1900. He's a coal miner, which is not great. And we can see he's from Wales. He's living as a son-in-law in his father-in-law's house. And then he shows up again in 1910, and it's pretty easy to find him. Again, we have a James Alexander. He's aged, let's see, he was 28. Now he's 38. That makes sense. Good. He's not experiencing much intergenerational or intra-generational mobility. He's still a coal miner, but I guess on the plus side, he's still alive. And so sometimes this is really trivial, and it works really simply. But this can go wrong in a bunch of different ways, right? There could be 20 more James Alexanders from Wales with about the same age. What if instead of finding one who's 38 or 29 instead of 28, we could have found somebody who's 29 or off by a year or something? What if he decided to go by Jim, or actually this happened when my co-author wrote these slides the first time. He was calling him Alexander James, because mixing up sort of the first name and the last name. All sorts of other problems can emerge. And we want some method that's basically not so brittle that it's only going to find 1% of people who manage to get their name exactly correct in every census. And so the Federal Census is a beautiful treasure trove of information. So this is 1940. We can see all these things are going to get eventually filled in. Years of education, earnings, what industry you work in, what occupation you have. There's special questions about what language you speak at home. There's questions about ancestry. A huge variety of things, plus everything we can see from who your neighbors were, or what kind of town you lived in, or what enumeration district you were in. But to do this, we've got to sort of go through the hassle of creating these link samples. And so classically, one sort of big important feature of this is all of this is handwritten. So these are enumerators from this Bureau of Labor Statistics report. This is literally not a person responding to the survey. This is the person who recorded the survey, the enumerator herself. And what we can see is that people write very differently. So the people in the bottom row have very sort of clean and simple handwriting. Helene Pollack writes in block print, which is really important. And the match rates are really much different depending on, again, just the quality of the writing. The simpleness to read, right? Someone had to transcribe this at some point. So if you're transcribing block print, it's just much easier. So names are going to be weird. Names are going to be messy. Here's the Feigenbaum version of this. This is, I think, the 1910 census. I actually don't think these are related to me, Feigenbaums, but whatever. The father in the household is pretty obviously Nathan Feigenbaum if you read it carefully. The census transcriber, so this is the raw image, but at some point, genealogy companies that I'm not allowed to criticize by name transcribed this data, and they managed to transcribe it as Mother Feigenbaum, which is not correct. The son is recorded as May. The border is an Isa. This whole family, not in this year, but in another year, is referred to as the Feigenbaums. And so this can be really challenging. You can imagine that it's sort of differentially bad for different types of people, and that's something we're going to come back to in more detail in a little bit. And so again, we need some method that's not just going to be a simple merge function. So last names and first names are sort of tricky. This is data that was linked by Dora Costa and her research team. These are basically linked by professional genealogists at an insane number of hours per link. Each of these data points represents quite a lot of human suffering. And all I'm graphing here is basically the string distance in first name between two of the sources that the Union Army is linked between. And what we can see is if everybody had the same name in all censuses, you'd be down here at the 0,0 point. We can see there's lots of people, including some people whose names seem totally uncorrelated year to year. And so again, we need to sort of have some method that's going to account for this inherent mess. So you can think of it in its simplest version as basically how many edits to the characters we have to do to change. So like Michael with the A and the E flipped would be like a string distance of 1, and then this is just scaled by like the length of the string. There's a few different methods for measuring string distance. We tend to, in the linking stuff, use this Jaro-Winkler distance. Okay, the other sort of challenge, not just names, is that ages are also always wrong. So the census actually doesn't usually ask for your year of birth. It usually asks for your age, which is another problem because sometimes it asks you for your age in April and sometimes in January and sometimes in June. And so someone can age by 9 years or 11 years or 10 years depending on whether or not where their birthday hits relative to the census date. But people are also getting this stuff wrong. There's a lot more people throughout much of the 19th and early 20th century born on years that end in 0 and end in 5 than is like logically possible because people are age heaping on sort of round numbers. The ages and the years of birth are also sort of like the hardest things to transcribe. If you're not crazy, like you probably know the list of first names that are possible. And you probably know that Mother is not a common first name. And so there's some context to help you transcribe names. But for numbers, I guess the age column is here, like, you know, is that a 19 or a 17? It's really, really hard to tell. You just have basically one shot to try this. Please. Which part? So yes, that's a great, yeah. So I'll have a slide on that later if anyone would like to, it's all manual currently. I think one area of obvious gain is that the transcriptions of these are not perfect and that moving this to a more automated procedure, which is above my pay grade, I work with the data once it's already become computer files, could have significant effects. My understanding, but people in the audience probably know this better than I do, is that like reading numbers, computers are pretty good at. Reading cursive names, less good, but maybe we've gotten better. What's up?
That's why you go to lens.
Oh, yes, that's why I got the lens. That's exactly. I'll have to get more of these for my RS. So in that sense, like year of birth is very much not exact. So Joe Price at BYU has like basically a team of undergrads that he's trained to do really good record linkage. And when they link people across the census, what they find is that about half the time, the year of birth distance is 0, which is to say people are aging 10 years from census to census. But that's only half the time. About a third of the time, they seem to not age enough. Sometimes they age too much, and this distribution goes out. I've actually cut off the people who are, for weird reasons, like seem to be way different ages, but the human who's done the linking is pretty confident this is the same person. So again, we have all sorts of problems with this. And then of course, as economists, the thing that I guess we care about, and maybe the rest of you do too, is if we build our data, if we build our analysis on weird biased data, is that going to affect what we're doing at downstream? Like I actually don't really care too much about building these linked samples, only so much as I can then ask a question with the linked data. And it turns out the answer is like yes, yes, yes. So one simple thing you can imagine doing is like, well, if I see you in Iowa in 1915, maybe odds are you'll stay in Iowa in 1940. And so what if I only looked for you in 1940? And if I was doing this by hand, maybe that would be a sort of a trade-off I'd have to make, because like looking through census manuscripts takes a long time. Turns out that can really lead you astray. So the sons who stay in Iowa, it turns out the prevailing wage in Iowa is like $30 or so, and a lot of guys earn exactly that. And the national distribution is similar, but it's sort of much less single-peaked. And so you can imagine you'd make a potentially incorrect conclusion about the returns to education or inequality or whatever else you're trying to study if you kind of screwed up in the census sample that you built. Same thing with some people, I've received this in more referee reports than I was expecting to, this simple panacea of like, well, just match people exactly. If you're looking for a Bart Lippman in the data, don't try to pick the Art Lippman, who might be a bad transcription or just a wrong choice. Only make the exact links. The problem there is you're again getting a weird selected sample. So when you do the sort of exact linking, turns out you find people who like get married and stay married at sort of higher rates. It's a different group of people. They're different in a bunch of other dimensions as well. So okay. A lot of things can go wrong. Maybe this is the point of the talk where you're like, screw it, I'm just going to use contemporary data. Like this history thing seems really hard. People are just going to complain that it's not important anyways. Maybe I should just like try to get administrative data from the IRS or something. But if I haven't totally dissuaded you, despite all these things going wrong, we want to figure out how we can at least do this a little bit better or try to do it better. And so ultimately we're going to face this obvious trade-off, right? There's the type 1 error when we say that two records are a match, but we were wrong, this sort of false positive. And then we have this false negative where there was a good match out there and we didn't make it because we were afraid of sort of how bad the transcription was. And so we're trading that off, right? We could only make type 2 errors, and we could basically say that everybody we link is a correct link and force our type 1 errors to 0. Or we could just link like crazy, get a bunch of bad links, but sort of really reduce our type 2 errors. And so in some sense, we have to decide where we're going to live on that trade-off frontier. And so generally, we'd like to sort of pick the right spot on that, but we'd like to have a record linkage algorithm that's going to be efficient in the sense that it's not going to leave a bunch of links on the table, sort of reduce those type 2 errors. It's going to be accurate. The links that we make are hopefully going to be correct links. We'd like to have something that's pretty unbiased, which is to say it shouldn't be super predictable who we're going to link and not link, although it turns out we can probably just reweight on the end to like kind of deal with that. But I also think, and this is sort of where the sort of the data science computing aspect comes into this, is I like to think that there's a bunch of other features that we'd really like to have. Maybe not from a statistical perspective, but from an academic or a researcher perspective, right? We'd really like it to be fast and cheap. We'd like it to be fast because like I don't have all day to wait around for my data to get built. But we'd also like it to be cheap because like I don't just want professors with big research budgets or teams of undergrad RAs in a basement somewhere to be generating linked samples, to be working on this sort of like cool longitudinal historical data. Ideally, it would be cheap enough that like a grad student could get this going themselves, on the side. And we'd also obviously like it to be nice and consistent, nice and replicable. There's lots of linked data probably built in the great span of history that was basically built because so-and-so's RA thought that person was a link for that other person, and then that decision point was lost to time forever. And when you try to understand why the data looks the way it does now, you have absolutely no idea. And so we'd like a system that's basically an algorithm would be nice that can consistently and replicably do whatever it's going to do. And then last, sort of, it would be really nice, and I think this is one of the features what I'm going to talk about, have something that's flexible. Which is basically to say, I'd love to be able to link in the 19th century and the 20th century. I'd like to be able to link the U.S. census, but also maybe the Norwegian census, although maybe that already has IDs, or the German census or English parish records, or from some state to the federal census. Like I'd like to be able to do a bunch of different things with this method. And so if it's only going to work on census to census linking, that sort of reduces the usefulness. So there's been a little bit of a fight, and I'm cognizant that I'm being videoed for this. There's been a little bit of a fight in the linking literature. Martha Bailey and co-authors had this paper a couple years ago that suggested basically all these automated methods are flawed, and really the only solution is hand linking. And I think of what I'm going to talk to you guys about is a little bit of a response to that. For a bunch of reasons, but I think the biggest one is I don't think that hand linking is actually the sort of solution to all of these problems. If we're going to link all these records by hand, it's probably going to be pretty accurate. And we might even eventually find everybody, but it's going to be really, really slow and really expensive. And I think even sort of just as problematic is it's going to really depend on the choices made in one moment in time by that researcher, or maybe by the 5 RAs who are all fighting over who's the right link to make. But it's not going to be as transparent as an algorithm that's going to be able to say, you know, this link was made because these set of criteria were satisfied, or because this score was sufficiently high, or this score was sufficiently low. And I also think, again, the slow and expensive part, like, if we all have to do this by hand, there's never going to be another grad student who does economic history ever again. And I'd like to not end up in that world. I'm all for like barriers to entry, but they shouldn't be too high. So I'll just say this is, you know, my method's sort of not the only method that's sort of going on like this. Abramitsky, Bustan, and Erickson have sort of a different method. This is getting a little bit weedsy for basically everybody except Bob in the audience. There's another method, Santiago Perez, there's a Davis, sort of a bit more Bayesian, I guess. But I'm going to talk mostly about my sort of machine learning approach to, you know, essentially doing record linkage. The idea that we can basically give an algorithm a bunch of data, and we can train it to make matches like a human. We can basically turn what used to be like my team of RAs. When I was a grad student, I taught a class and then immediately hired some students who, like, not the best students in the class, but like some good students from the class, and had them do hand linking. But the problem is that they were really expensive. And so that eventually I realized that I ran out of money, and I had to figure out a way to teach a computer to essentially do what they had been doing. It also turns out the computer sends you far fewer emails with questions, which is good. So that's a big benefit. I didn't put that on the slides. So okay, so what do I actually do? Again, the idea is we're gonna replicate how this well-trained and sort of hyper-consistent RA is going to do the work. The key thing here is it's taking all these implicit rules, all the judgments that you would make as a human, comparing two names and being like, is this the same person or not? Or do I think this is more likely than not to be the right people? And then make those rules explicit. It would be really hard for you to write down all the things that you implicitly do when you make that judgment, but it turns out if we give an algorithm enough data, we can write those rules down explicitly. And so the procedure is actually really simple, and this is sort of the only math I'm going to show you. And there's really not even math. Basically, we're gonna go looking for some son from the Iowa 1915 census, for example. And we're gonna find all the people in the Federal Census in 1940, or wherever we want to find this guy, who could be him. And this is, again, I'm sort of being loose about this because you could define this blocking criteria or this first net. You can cast this net wider or smaller. It's just a question of sort of computational power and how many names you want your RA to have to read through when they build the training sample. So we're going to find all of these possible matches. We're going to manually select some matches for a small training set and build that training set. And then we're going to use an algorithm to basically approximate all those manual linkage decisions. And we're going to use, the human doesn't have to necessarily know they're using string distances or sound scores or character matching or whatever else we're going to plug into this. The human just has to look at two lists and say, like, this is this person, this is that person. And then the algorithm's going to try to build up, based on all these different features, how do we think the human made those choices? How, basically the thing to think about is like a name that's off by one character in a first name versus off by two characters in a last name. Which of those gets a bigger penalty? Or the names are exactly right, but the year of birth is off by 5. Does the human think that's still a good match or not a good match? And maybe that depends not just on the records we're comparing, but on 10 other records on the page that suggests, like, you're the only person with this name in the whole world, and so you must be the match, even if your year of birth is off by a little bit more than I'd usually tolerate. So these things can sort of interact, and the function can be quite complicated. And then we apply the algorithm to the rest of the data. So this is the part where I'm about to have to defend why I'm going to call this machine learning, even though I'm just using a lame Probit model. which is something, again, I get in referee reports. But again, we're just going to do a really simple two-step procedure. We're going to regress whether or not you were a match on a bunch of features about your link, so the string distance and the sound scores and a bunch of other things that sort of describe whether we think two records are the same or not. And we're going to draw a bunch of data from the hand linkers, and we're going to sort of, taking those careful human-made links and figure out how to make matches. Okay.
At this step, you
Yeah.
do a more machine learning thing that your mate would make.
Yes, I know. You probably could. So this is what the guy said. I assume guy. Basically, this isn't actually machine learning. You're just using a probit, which isn't wrong. Like, I am literally just using a probit. I think so. The defense that I think I've come to, I think, there's a couple different versions of this. But at the end of the day, what I'm doing is there's a super implicit, vague procedure that humans are doing, right? They're comparing these two lists of names, and they're figuring out who's the same. And there's a bunch of decisions made, but it'd be really hard to write down a full set of decision rules that would make those rules explicit. And so in the sense that I'm doing machine learning, I am teaching the machine is learning from the human's data how to make those choices. And like, however simple my model is of the choices being made, it's still, the data is teaching the machine how to do what it's doing. Well, that's a whole different thing. I'm doing machine teaching, but the thing is a machine that is learning. And so Danielle is actually absolutely right. Like, there's a world in which this is a pretty simple function, and I could replace this with something fancier. This may be. I'm happy for any of you who are more machine learning-y than me to yell at me over this. This does a reasonable job, and it's easy to explain, and it's not a black box. So I think it has some features that we like. But it's entirely possible I'm leaving some links on the floor, or on the table, or wherever I'm leaving them, that I could be making were I to use something a little bit fancier than this. But I think the value I'm getting here is it's I can explain exactly which features matter and what drives what.
So for those that are not versed in the more advanced machine learning methods,
Yeah.
is one of the advantages of what you're doing that it is consistent, that some machine learning methods will not, given the same data set, will not necessarily predict the same match, or is that sort of order dependent?
Oh, that's interesting. Yeah. So I think in theory, I don't have a scientific answer to this because I've basically done this a lot, and I've played with other options for other models or other ways I can do this. You will ultimately get every different model is going to give you slightly different predictions or slightly different choices of who's going to get matched. I think the biggest feature here is because it's a probit and I can actually look at the coefficients. Most other machine learning, like if I run random forest on this or XGBoost on it, I can do a little bit to try to squint at which features are driving predictions, but not nearly as nicely as I can when I get a set of coefficients back. So I think that's the key sort of feature of this.
I guess the question is, if you're doing random forests,
Yeah.
will it give you the same results if you apply the procedure twice?
Oh, yeah, it should. I mean, if you fix the seeds, you could play around with it enough that you could probably get a little bit different. But if you do the things that you're supposed to do about fitting seeds, then yeah, it should be consistent in that sense. Yeah.
All right, so
Please.
This is one-to-one matching. So the fact that you match with someone means that someone else is going to be matched. So are you going to maximize the sum of the?
Yeah. So this is actually a feature in which I think that I'm currently doing. I'm sort of dealing with that problem in a pretty ad hoc way that I suspect actually more structure would be pretty valuable. And so maybe we can talk about that after. Yeah. So it is one-to-one matching, right? If which is actually not technically true. Sometimes people can get double enumerated or something, but generally it's one-to-one matching or 1-to-0 matching because people die. But it's very sad, but they do. So the probate actually doesn't sort of know the exact dimensions of the problem. They don't know that if I link John Doe to one record in 1940 that he shouldn't link to another record, or vice versa, that whoever I link to John Doe in 1940 shouldn't also then link to other records. And so basically there's sort of a second step is I'm going to use the probit to basically give me a score, and I'm going to declare you a link only if your score is sufficiently high and it's sufficiently larger than sort of all the second best matching. So I'm enforcing the one-to-one stuff only in sort of this ad hoc secondary stage in what is, a doable procedure, but perhaps almost certainly not the optimal one. Michael?
So James, what you're talking about is increasing accuracy, but there's still a problem of selection and bias. And
Oh, yeah.
For example, if you take a name like Kulicek,
Hypothetically.
it sounds kind of Slavic, maybe from the Czech Republic or somewhere in Bavaria. And that's going to be easier to match because it's a more complicated name than, say, Lang. There might be
Yeah.
a lot of false matches, and you can get bias about origins. Or
Yeah. No, I think.
how do you get rid of that? I mean, that's going to be true with humans and machines.
Yeah, no, I think that's, so one fundamental truth is like a John Smith from New York State, I'm almost never going to match. Or a Ben Cohen from New York State in 1900. There's 40 of them, and there's just no way to distinguish between people. There's going to be a set of people that are just basically, because their names are just too common, are not going to be matchable. There's also going to be people whose names, the foreignness and the name commonness is tricky, because actually if your last name is sufficiently foreign and unfamiliar to either the transcriber or the enumerator, it could get entered with such error that, again, I'm never going to find you. So sort of this double-edged sword. So you're right, there's going to be some selection in who we're able to match. I think the best and sort of only response to all of that is we're going to try to, we have all these variables, we can try to predict exactly who we can and can't match, and then we're going to have to reweight at the end to try to make our ultimate link sample as much like the sample we started with. But of course, there's going to be like, if you really care about the economic plight of people who have incredibly common names, this is not going to be, I'm not going to be able to answer a question about like the return to education among John Smiths, because there's just not going to be any John Smiths in my data. Yeah. Okay. Ivan, did you?
So how do you choose like to put in the X's, right? Because that's key. And the other question as well is, isn't using the Probit cannot be a problem of overfitting, that if you put enough X, it becomes really...
Yeah. So I would say the main guardrail or speed bump against overfitting is just like there's not that many things I observe about people that I think are like sort of clean variables to predict whether or not I'm going to link you on. I'm mostly going to rely, the things that are doing most of the work are these string distance measures. So essentially how many typos, how many edits to go from one name to another. Sound similarity, so like, this is a world in which like Ivan and like Evan would get the same soundex score, and so it's totally plausible that like census enumerators are messing that up when they write it down, or transcribers are messing it up, so you're going to get more likely to be matched. Whether or not like the first character matches, whether or not turns out whether or not the last character of a first name matches or not is pretty predictive. For some reason, people pronounce those pretty well. How common your name is, again, so you might, if you have a really, really uncommon name, we might be willing to give up more string distance or more year of birth distance. Again, these aren't trade-offs I necessarily know going in, but I give the machine enough data, or I give the Probit model enough data and sort of try to make these trade-offs. There's also a bunch of stuff that you probably don't want to include. Like I said, you really don't want to include things that we think are sort of endogenous or might change over the decades. If I want to learn about how people's occupations change over their life, I probably don't want to link a sample based on what occupation you were in, and does your occupation match 10 years later. You'd be amazed how many people fight you on this and think that like, oh, but I can do so much better because I have all these other names of all the other people in your household, but if I used your spouse's names or your kids' names or their ages, like all of those things are going to select me towards a certain group of people in my data, and maybe going to screw up sort of what I want to say about them. Okay, so we use the Probit scores. I want to actually jump ahead through. So how does the model do? So you can think about sort of two different criteria to evaluate this stuff on. Basically, the true positive rate is sort of like 1 minus the false positive rate. Makes sense. Basically, how accurate are we? These Probit models, at least in this Iowa 1915-40 data, tends to do about 86%. Sorry, this is there. Positive predictive value is much more like the accuracy. This is much more the efficiency. How many of the matches that the human made was the computer able to find? Both of these are going to be in the sort of the upper 80s. And obviously you can imagine twisting some parameters. If you really, really care about this and care less about this, we can drive this number up and consequently drive that number down, or vice versa. We're all sort of living along this frontier. In this new paper with Rana Bromitsky and Leah Bustan and Catherine Erickson and Santi Perez, we compare all of these different methods to this Union Army sample. Again, this was linked by the professional genealogists. We asked for an actual number of how much it cost them per link, either in time or in money, and they did not share it. But my understanding is it's extremely, extremely high, like days to link one person. We could FOIA a grant with some dollars in it. Yeah. So where are we living? So the hand linkers who train the machine are here. This is, I should say, these are hand linkers who are seeing what the algorithms are seeing, and then we're comparing everything to the hand linkers who are the genealogists who see everything. How do we end up doing it? It turns out we end up tracing out a little frontier across the different methods. So there's a bunch of methods I haven't really talked about. They tend to be sort of over here, much sort of lower TPR, which is to say they're leaving a lot of matches in the table, but extremely accurate. And you come out here, and our pink triangles are the sort of my machine learning method. We're sort of, again, trading off. Maybe we make a few more bad matches, but we collect many more of the matches we had. And sort of not surprisingly, we're reasonably close, although probably it could be closer, to the hand linkers. Again, the machine, the ML method is, the whole point is it's learning how to do what those hand linkers were doing. And so, yeah, I guess I was supposed to click ahead to that slide and show you that.
I mean, you talk about genealogists. Are they academic types?
Oh. So full disclosure, yeah, hand linker, like that's me, and that's an RA that I hired 3 years ago. No, they are not professional. They have received training to some extent, and the other thing is that they're not genealogists in the sense that they are not using all the available data. They are literally seeing the person's name, the person's state of birth, and year of birth, and just on those characteristics, and they are told, you can make a match, you cannot make a match. The whole point of this exercise is to use the human's best judgment to who the match is, if such a match exists. Randy?
Is all the work you're doing using the already digitized name as in a letter, or can you look at the handwritten copy?
That's yeah.
Obviously, knowing the enumerator, you can look, they use a lot of squiggles. Hands put an extra curl.
Yes.
Which one are you?
That's a fantastic question. So this is all based on the data is already transcribed, you receive the transcription. I think, and probably to our detriment, we've sort of separated these two problems, like getting better transcriptions from figuring out who's who in the data. It is almost certainly, you're almost certainly correct that like different enumerators have different styles, that some are more likely to mistake M's for N's, or like R's and N's turn into M's, all that kind of stuff. We're sort of putting that in the background. I think, and I'll show you in a minute, like transcription is really hard, and so I think that's where a lot of the problems are sort of coming from. Yeah?
The other example in your talk was if they look and say, oh, it's a head of household and it's male, then you would rule out mother as the first name, and you
yes.
would look across fields. It doesn't
yes.
seem like you're doing that.
So yeah, so we're basically, you're observing the name, we're only linking men, and I'll talk more about that, probably not at the end, but I'll give you 10 seconds on it. But yeah, we're using the fields as we get them, and that's sort of going to lead to potentially some problems.
Sorry.
Yeah, Kiara.
Your algorithm is also using the name of the transcriber or no?
No, so in the end,
I don't really need to go back, it's just
yeah, transcriber fixed effects. That's an interesting point. Yeah, so I think that in the census there are a lot of enumerators, and the transcribers we don't know. We sort of again, it's sort of this black box that like we have raw data, but the enumerators right now we're not making use of it. I don't know if basically. I don't know how much training data you would need to get like enumerator level fixed effects, or sort of you might have to train the entire 100 million to 100 million census link to get those, and at which point you've already done all the linking. Okay, so that was a comparison. Again, the truth here, the we like to say put ground truth in quotes because humans are fallible and even the genealogists make mistakes. They got to see lots and lots of variables. What happens when we compare the algorithms to sort of the things that we usually see in a census, the basically names and state of birth and age? It turns out when we sort of make the comparison more fair, we sort of find a little bit of a different result. Again, the accuracies are quite high for some of these algorithms, and the TPRs are quite low. This is a place, actually, when we're comparing the automated methods to the sort of limited information human linkers, we tend to do really, really well. The ML method does a really good job, again, of capturing the people that the human was able to link, and of basically getting a lot of the people that the human was able to link, and getting them sort of correct relative to how the human did. OK, I just want to, again, flag, like, this is hard. So these are actual examples from the Iowa to 1940 link sample. So this is Guy Paul Coulter. I don't know, probably not anyone's grandfather. Born in Kansas in 1912. The human liked the link to Paul Coder, and one of the algorithms liked Paul Corder, born in a slightly different year. William J. Lyons, should we be linking him to William Lyons, born in an incorrect year? Or are we going to suffer the difference of a middle initial to get the same year of birth? And so some of these are edge cases, and maybe your argument is that we shouldn't link anybody. We should just count these as zeros, and there's plenty of those also. But sometimes it's really hard to know who is making the right choice. OK, so let me flash through a little bit to the sort of where I think this is going, and maybe afterwards some of the people who are much better at data and machine learning than I am can help. So yeah, is moving beyond Probit like a useful feature of what's going on here? I think, again, I like the Probit because I can explain it to almost anybody, and I can explain it to myself, which is maybe even more important. But maybe there's value to supercharging these machines. There's like a reason that Google doesn't try to do image recognition with Probit models, I don't think. And then the other big thing is basically this has always been two steps in the sense that we build this linked data and then we run regressions with it. But maybe we're screwing that up. Maybe we should keep around the fact that I was 100% sure that I found Kevin in one data set, but only 80% sure that the Michael I found was the correct Michael. And so maybe I should be keeping that uncertainty around for when I'm doing stuff later. Again, it seems obvious now that I say it out loud, but something we haven't been doing. And of course, the features can always get better. So one thing that I'm actually working on now with Joe Price at BYU is basically using the genealogy data to generate sort of a data-informed dictionary of name changes, understanding which names can be linked to others. These are trivial and sort of obvious, but once we get beyond the most common 100 names, how do we know what kind of who gets, what names sort of get Americanized, or what names get nicknamed or transformed over time, or even just typoed over time? Obviously, yeah, more features applying to other locations, and then the last point is that it sometimes takes a long time to do this. And sometimes I get yelled at by the people who run the server where all this data lives. And so possibly this could be faster and more efficient. OK, and generally, one thing that I think is sort of on the that I don't know the answer to is basically I essentially build a new training sample every time I want to use this. So when I have a project that wants to link people from Iowa 1915 to 1940, I build a sample for that. When I do another one for the members of Congress, I build another training sample to link them. Is this duplicated effort? Is there some way to build a model that's essentially good enough to use all over the place? A one-size-fits-all kind of thing. OK, so I want to flag one more fun result, and then I don't know how this question's been happening during, but I'll try to shut up and let you guys have questions after. So why is linking so hard? So this is from that paper with Ron and Leah and Catherine and Santi. And one of the main reasons that it's really, really hard is basically cursive is really hard to read. Those of you, I had, I think 2 students last semester who wrote exams in cursive, and it was really, really hard to read. And I just gave them better grades because I felt like probably it was right. Yeah. So anyways, one way that we think this is true, we don't really have a good way to test, or at least we didn't. And so what we did is realize we could try to answer this question. So we have 2 copies of the 1940 Federal Census. It's the same raw images, same cameras took pictures, digital images of these censuses. One was transcribed by Family Search, and one was transcribed by Ancestry.com, 2 different genealogy companies. They varied quite greatly in who did the transcription, and that's all I'll say for now. And so we know who the links are because we can basically put the spreadsheets on top of each other. So we know who should be linking, and what we're just going to ask is who did link. No one's going to die because it's the same file. No one's going to actually change their name. This is purely going to be about transcription. And so what do we learn is that people are really bad at reading cursive. These are the Jaro-Winkler scores, first name on the x-axis, last name on the y-axis. And again, if the transcriptions were perfect, all the mass would be on the 1-1 spot. And what we can see is that's definitely not the case. And it's differentially not the case, right? So Iowa, people who were born in England, actually they're doing okay. We can see for the Italian graph, there's a lot more people off of that sort of 0-0 point. We do this in the paper sort of by race. There's actually much more transcription error, perhaps not surprisingly, for African Americans than for whites. And so we can see that a lot of these errors are going to potentially make us unable to link somebody, right? If your name is so hard to spell, so this is first name distance of 0 but last name distance of 1, that I totally butcher your last name, it's going to be really hard to make those links. And so when we do the link, again, census to census, itself to itself, we're only able to match about 50%, depends on the method, which suggests that both those common name problems and those transcription problems are really kind of creating a strong upper bound for us. And so maybe that's where improving the transcription would help. I couldn't get the footnote to only appear when I clicked the button, so it's just for a while, it's just saying, please help. But like maybe this is a solvable problem. Maybe teaching the computer how to read cursive better is a feature that we can push forward to. Okay, so ultimately we want to actually do science with these things. I usually just say economics, but if you caught that, I was being very interdisciplinary. So social science, whatever. And so we might be really worried that the actual analysis we're going to do is going to depend on what method we use. And I'm going to skip through this, but like the point is it actually doesn't seem to matter. Like we fought a lot over the right way to do linking, but it turns out when we run a bunch of regressions, like this is just your occupation score, sort of your social status in 2 different points in time. No matter how I do the matching, I get basically the same result. I actually showed you that first graph way a long time ago of the return to education with the paper with Huiren. And there again, whether we do the my matching or the ABE matching, we tend to get basically the same sort of qualitative answers. Similar thing, there's not a lot of good regressions you can actually run in this Union Army data. I don't know why they spent so much time collecting it. But you can do height effects on status. And again, we get a sort of noisy 0, but you can see the coefficients are sort of all stacking up on each other. Okay, so let me just conclude a little bit with sort of the next step. So how do we improve the linking algorithm? And then are there sort of alternatives to linking? And so 2 features I think that are really important. Basically, everything I've told you so far has been about white men. We're really good, or at least good enough, at linking white men over time historically. It's really hard to link African Americans in the census. So there's no enumeration during slavery, at least no enumeration by name. And then post-emancipation, there's lots of age heaping. There's lots of common name use. It's just the match rates are much, much lower. And so people tend to have focused on the white sample. And then for women, of course, there's like the predictable problem of in the early 20th century, the name you had as a 15-year-old is probably not the name if you get married that you're going to have as a 35-year-old. And that's just a really, really hard problem to deal with. And so I'm going to pause for questions, and if there aren't questions, I'll give you my like half answers to both of these challenges. Or I'll have cowed you into not saying anything, and then you'll let me talk for another 5 minutes. But Kevin.
Broader question.
Please.
Why do you insist on there being only one match as opposed to
I think for bad historical reasons, that's sort of the way we've always thought about it. It's not obvious if you're trying to link somebody, like there's a John Smith and there's like 30 different matches, it's not obvious that including each of them as like a 1/30th weight is the optimal choice. But in a world in which there's only 2 and we're reasonably sure, or there's one person we're pretty sure about and someone we're less sure about, yeah, it's not obvious to me that sort of a more probabilistic strategy wouldn't be a correct thing. And all of the methods, well, I shouldn't say that. At least the sort of the machine learning based method approach is going to return to you scores And so if you had a clever thing to do downstream with those probability scores and could, wanted to keep that uncertainty and keep that weighting, you could do it with it. But I think that we just, basically no one's made us do that yet. And so we've been more invested in making the links and less invested in figuring out ways to sort of deal with the uncertainty or the multiple matching.
Without having thought through the kind of metrics, for people who are knowledgeable, I would have thought that if you had a posterior, that there was a 50% chance that this was the right match.
Mm-hmm.
Right? You just want to include that match and downweight it compared to one where you thought it was a 99% chance.
Yeah. So I think the challenge, so I think
And that'll depend on, your posterior is going to depend on all the other matches. So
Yeah.
in that example, okay, we've got 30, let's assume they're not absolutely equal, right? You'd have one that at a .04
Yep.
chance of being the right one as your posterior.
Yeah. And so I guess the question would be at some level, would you rather, match all of them and weight across them, or match none of them, or split the difference somehow? It's not, you'd have to, I think you'd have to write down, you'd have to sort of have some preferences over something to figure out which direction you wanted to go. But the current thing we're doing is certainly not no one's written down a theorem to prove that this is the right way. Here.
Yeah, I think one way to go is probably take a probabilistic approach.
Yeah.
If you are not sure about whether you can take a stand and pick one match or the other, you may want to see what you observe as a set value observation. The truth is
Mhm.
in there, but
Yeah.
you see a set of them.
Yeah.
So it could be the case that you may want to include someone whose middle name is different or whose birth year is different.
Mhm.
They are all in the set.
Mm.
And so the truth is somewhere inside, but you don't know where it is. There are now methods out there to use set value observations as primitive objects
Mm-hmm.
and then try to make inference
From that.
from that.
Yeah.
You typically lose point identification. That's the price you pay.
Yeah.
But that could still give you potentially some informative
Yeah.
understanding. Seeing the results you showed us.
Yeah.
The results do not seem to vary too much.
Yeah.
By changing how you select a particular
I see.
match. And so it could be the case that the bounds are pretty tight.
That's interesting. Yeah. I'm not sure how, so my only fear would be these methods are all playing within the same world that Kevin doesn't like, of trying to make the links that way. And so you might be, when you jump outside to these multiple match guys, that we then have a set of them that this doesn't inform that, but you're right.
Set to keep them.
Yeah.
That's still something you need to
Yeah.
where to stop.
Yeah. No, that's a great point.
On
Bob.
that one point, though,
Yeah.
there is a fundamental issue that is that you don't know for sure that the truth is in the set.
Yeah. That's a great point.
Yeah, that's true.
Yeah.
That's something I was maintaining.
Yes,
That's
I mean,
something,
John Smith, you might link to 30 John Smiths, but you don't know for sure
Yeah.
that the actual true John Smith is in the list.
Yeah. Our John Smith could have died. He could have moved to Canada. He could have changed his name. That's right. Yeah. That's so. The truth may be out there is probably the right the tagline on that. Yeah.
Two just high-level comments.
Please.
One regarding machine learning. So I sympathize with the reviewer comment. Partly because machine learning as a term, there's so many cultures that
Yeah.
are involved at varying degrees of depth or feelings of ownership or lengths of history. And all of that comes together sometimes in weird, cryptic comments. But I think you can elevate that up, and with a reasonable reviewer, it should work. Unreasonable, good luck. But elevating the discussion, is it machine learning? Sure, look at any intro textbook to machine learning. It starts with linear regression,
Yeah.
logistic regression. Probit modeling is a short hop from logistic regression.
Yeah.
There's some reasons why you would do it. This also blends in the sort of return to interpretability now. That's just one
Yeah,
thing.
that's right.
What had as one of its strengths was poo-pooed for a while in a predictive era, and now is coming back in the forms of interpretable AI.
That's right.
So there probably is a reason and concise way to just say, it's a simple one.
Yes.
It's not quite a weak learner in the formal sense, but it's
Yep.
a simple
That's right.
learning algorithm, which are not unknown even in the model era Kaggle competition. For
Right.
example, there was one recent Kaggle competition where a slightly
beat everybody. Or,
It's just almost beating everything.
yeah.
So it's not unheard of at all.
Cool.
The other conversation
Yeah, please.
In my role is sort of very directed and
Yeah.
to create synergies in what if you don't know Jacob Bohr and Alana Brennan
Okay.
on the Med campus of Global Health.
Yeah.
They are working with data from South Africa where they have various specimens from individuals across time that are recorded with varying degrees of fidelity, accuracy, and they also are moving, so you have human mobility that's coming
Yeah.
in. They've been talking about the people in computer science and recently myself on the question of uncertain propagation.
I see. Okay.
It sounds like I'm hearing some of the things where they've
Yeah.
spent a long time on the record matching record linkage, and there is the uncertainty. Digging into sort of is there a literature, which I'm wrapping up myself finding there is actually somewhat.
I see. I'm bringing that forward.
Well, so there's interesting synergy with algorithms.
Oh, that's interesting.
So there are probably more people on campus actually that,
Cool.
from a horary perspective, if there's a group that wants to talk or something.
Yeah. All right. I'm always available for lunch.
It won't be at the Ritz.
I'll manage. Cool. All right, I'm going to give you 2 slides on the next thing, and then I'll let you go. So this is work with Chris Muller, who's a sociologist at Berkeley, and Suresh Naidu, who's at Columbia. And so this is super preliminary. We're sort of trying to understand or to see whether we can use census linking, but also sort of name data to understand a little bit more about enslavement and sort of the immediate postbellum period. And so the basic thing that we don't know is if we see a black family in 1870 say in Georgia, who and how long had they been enslaved? Were they free during the antebellum period? Were they freed upon the end of the Civil War? Like, what's the sort of the family history of this? So we're drawing sort of on some stuff that Daniele and Claudia Olivetti have done, using sort of first names as a signal of what your parents are like, but also sort of work that Ron and Leah and Catherine are doing to sort of understand first names signaling foreignness, basically. And sort of we're appropriating these ideas and these methods to basically try to predict a history of enslavement. The essential idea is if we see a bunch of new names in 1870, we think that those are names that are much more likely to have been given to people who had been enslaved and not previously enumerated. Versus if we see a bunch of names in the black population that had been in the free black population in 1850 and 1860, then we think that those are probably names that are not associated with people who have been enslaved. And so again, insanely preliminary results, but it seems like this really has massive effects. So this is how much property someone owns in 1870. You can think of these scores going from 0, as in almost certainly free in 1860 or 1850, to 1, almost certainly enslaved in 1850 or 1860. And we can see the mean of wealth is not particularly high. These are dollars in 1870. They're almost entirely erased, or more than entirely erased, by this sort of history of enslavement at the family individual level. We see the same thing for personal property. Effects are a little smaller. Similarly, occupation scores are lower. And then where we're really pushing this is, can we say something about this intergenerationally? And so we do this linking, even though it's hard, even though we lose a lot of sample. And we observe these children who are born right around the time of the Civil War. And we can basically ask, were your parents, had they been enslaved or had they not been? Or do we predict them to be or not be? And what we learn in a table that is much too small for any kind of a presentation, I'm feeling bad about it already, is that people whose fathers had been more likely to have been enslaved are quite a bit sort of worse off when we see them as adults in 1900. Same is true when we see them in 1910. Same is true when we see them in 1920. There's no effects apparently for the moms. And sort of we run the horse race, it all loads on the father's scores. And so this is just super preliminary. We're sort of combining some of these insights that it's really hard to do linking on some populations, but maybe there's other things that we can learn from the rich census data. And if you want to learn about how I link women, you'll have to talk to me later. Okay, so let me just jump to our conclusion. Thank you so much. And I think there's still coffee and cookies upstairs.
Yeah.
Cool. Thanks.